4.4, the mean value theorem, which starts at page 379. Now let's first look at Rolle's theorem. What is Rolle's theorem? It says if f is a continuous function over a closed interval ab and differentiable over the open interval ab, then, and also if f of a equals to f of b, then there is some number where f prime of c is 0. What that means is if you have a function, okay, and it starts at some point, okay, and it goes around and then end up at some point that's the same, okay, it end up at the same point. See, this is level. In that case, then at least at some point of this function, at least one, that this function has to be have a flat slope, a level, okay, have a level slope. This one I draw happens to have 2, but you will be able to find at least one, and that is Rolle's theorem. Now that seems fairly intuitively obvious, which makes this this problem easy to prove. This theorem easy to remember. And the proof isn't that much harder. So let's look at the proof. Okay, the proof says that we'll let the value of being the f of at a and f at b are the same. We'll call it some number k. We'll name it k. All right. And then we will prove it in 3 cases. Case 1, f of x equals to k. So case 1, f of x equal to k forever. That is just a constant function. Now, if it's a constant function, then of course f prime is 0, because for all constants, f prime is 0. See, f prime of x equal to 0 because f is a constant function on the interval that we consider. So that's a given. That's an easy case. Now, this case 2 is for at least one point, okay, on the interval. So for at least some x, there exists some x inside the interval that we're talking about. That means x is somewhere between a and b. Then at least one of the x's where f of x is bigger than k. That's the second case. So at one point it might go above what these things are, right? Now that's the second possibility. The third possibility is at least at one point that it is below the value of the constant. But we're only going to go to prove the second condition, because the third condition proves the same way. So let's look at the proof of the second condition. The second condition requires us to quote the extreme value theorem. Now, if you already forgotten what was that again, then I recommend that you copy down that theorem in some kind of notes. Just a quick notes that write down what is the extreme value theorem, and also the several theorems. We're going to cover about 4 different theorems in this chapter, and copy and paste these theorems onto a notepad or something on your computer, because that way you can refer to it instead of flipping pages in your book, which is not that easy on something like this. You can also do a search function, of course, but that's inconvenient. It's better to just write it down in notes. So I have it written down. I got the notes then. And what is extreme value theorem? Extreme value theorem is that there exists some absolute maximum and absolute minimum. Okay, so it has an absolute maximum and absolute minimum. The absolute maximum is so this function exists at absolute maximum, and being that at one point f of x is bigger than k, so first we will say there exists an absolute maximum by the by the, what is this? Extreme value theorem. Okay. So there is an absolute maximum. The absolute maximum is by definition then has to be bigger than k, right? Because there's a point x where f of x is bigger than k, so the absolute max is also bigger than k, which means it is bigger than the two endpoints because the endpoints are equal to k. That's our premise of the Rolle's theorem, is the endpoints are the same. So and the max is bigger than k, and which means the max is inside. So the absolute maximum is not on the endpoints, is inside the. So the absolute maximum is somewhere inside the interval, the open interval, a and b. That means the parentheses means that a and b are not included in this interval. Okay, that means belong. Okay, this belongs is somewhere inside the open interval and not on the endpoints. Now, and then next we are going to say that because it has a maximum on the inside and is differentiable, then by Fermat's theorem, f prime is 0. The Fermat's theorem is, I didn't write that down, but maybe it should if you can't remember what it is. Fermat's theorem says if the function has a maximum and is differentiable, then the derivative is 0. So which means there exists a point of f, there exists c such that, anyway, so there exists a c such that f prime c equal to 0. There exists c that's at the absolute maximum such that f prime of c is 0. And then and that is what we're trying to prove for Rolle's theorem. Now so in case 2, we considered where f of x is bigger than k at some point of x. The case 3 is f of x less than k, but the proof is identical. Okay, then you have an absolute minimum that will be less than the k you found, and therefore by the same by Fermat's theorem, then f prime c is also 0 because Fermat's theorem applies for both maximum and minimums. So with that, we prove Rolle's theorem. So let's go to the next page. So to repeat, Rolle's theorem says that there exists, if you have some function that goes up and down but land in the same spot, then you will have at least some kind of a place where the derivative will be 0. In other words, the slope is at 0. Okay, it's flat level. It's level, not flat, level. And that is the whole concept of Rolle's theorem. All right, now let's look at the next thing. Now, the using Rolle's theorem is in this, Rolle's theorem is mostly used for proving other stuff. There's no need to use it directly, really. For example, if you want to, let's look at example 4.14 on the next page. You have some function, right? And you want to find out when is f prime equal to 0. Well, that's simple enough. You figure out what the derivative is and set it to 0 and solve for x. So I will let you do that. That's example 4.14 in your homework. Okay, that's assigned. Yep, examples 4. Oops, where's 4. I did not write down 4.14. So I wrote down 4.14. Please do that as your homework. And then next, we will flip along and get to the mean value theorem, which is the whole point of this section. The mean value theorem, let me erase the board. We need space. Page 382, the mean value theorem. Now you might think, that sounds familiar. Did we already do this sometime? No, the one we did that sounds familiar is the intermediate value theorem. Sounds similar, very different. Okay, now this is the mean value theorem. The mean value theorem is similar to the Rolle's theorem in that the Rolle's theorem says that if you have a function that end up in the same spot, fa equals to fb, then the function will have a slope that equals to 0, okay, a level function. Now the mean value theorem says if you have a function that doesn't end up in the same spot, okay, like similar that, well, then what? Then what you do is you draw a line here, and then you will have a point where the slope is the same as the line that connects the front and the back. In other words, it's the same thing as this one, except tilted somewhat, but it's the same concept. Okay, that the slope, in other words, if you were to you just look at it sideways, kind of. Okay, it's the same as the Rolle's theorem. Is they will this is the same slope as whatever this is. All right, that would be the to be exact. It says that mean value theorem says let f be continuous over the closed interval ab and differentiable over the open interval ab. Then there is at least one point, at least one. There might be more. At least one point C on the open interval AB. That means it's not on the endpoints. On the open interval AB, such that f prime of C is equal to the slope of here is the same as the slope of here. The slope of here is rise over run, okay, which is in math is fb minus f of a over b minus a. So the MVT mean value theorem is written as f prime of some point in here equals to the rise, okay, the rise fb minus f of a over the run, okay, the rise over run, okay, rise, here's rise and here's run. That's rise and that's run, b minus a, where this is a and that's b. That is the mean value theorem. Now the proof of the mean value theorem, being that it is very similar to the Rolle's theorem that we did earlier, except it's tilted, the proof is also based on the Rolle's theorem. Now how would you prove that? First, we have we have this. The difference is, of course, now a is not equal to b. So now how are we going to do that? Well, we are going to pull off a trick. Okay, the trick is this particular function, and it is called, we'll pull out this trick, g of x equals to f of x minus this pile of stuff, f of b minus f of a, b, f of b minus f of a over b minus a times x minus a plus f of a. All right, so we have a pile of stuff, a long-looking function. It might be long-looking, but this is a minus. Okay, that should be good enough for anybody. Okay, that might be long, but it's not particularly tough function. For the function g of x is defined by f of x itself, and then this is that number right here, okay, which is a fixed number. This is because we know what the function f is, okay? So this is some fixed number of the value of f at b, and then at a, and subtract and all that stuff. This x, then we multiply this particular number by x minus a, and then add up f of a. Why are we doing that? The reason is because we're trying to use Rolle's theorem. Now, so we make up this particular thing. Why? For this reason. First, what is g of a? Now, if you calculate g of a based on this function, that will be equal to f of a, okay, minus a minus a is 0. That knocks this thing out. Minus f of a, right? So there's only f of a left. So then you get g of a equal to 0. All right. Now g of b, what is g of b? G of b equals to, let's plug b into the x. So E equals to f of b, which is that, minus b minus, that becomes b, all right? Okay, we will, if this becomes b, it can't, that's b minus a, that's also b minus a, so that cancels out. So we only have the top left, which is f of b minus f of a plus f of a. And what does that equal to? That becomes minus f of a plus f of a is 0. fb minus f of b is also 0. So this g of b has the interesting quality of being 0 as well. Next, we're going to do, what is g prime of x? Okay, g prime of x is, we'll take the derivative, okay? So f prime of x minus that thing. There's an x here, so when you take the derivative, we have that thing left, okay? So we'll copy that down, f of b minus f of a over b minus a. That's that's about it. I will put this, all right, yes, I'll put this in parentheses, all right, and then the derivative of that thing is 0 because it's a constant. So, and then, so now we have a specific function where it is 0 at a, right, 0 at b, okay, and its derivative is whatever. Now, by Rolle's theorem that we just proved, if you have a function that is the same at both ends, then there exists a point in G such that G prime equal to 0. G prime of C, there exists a point C where G prime of C equal to 0. And this is by Rolle's theorem that we just proved. Okay, so that means, so then we'll plug the C in here, which says that I'll write it on top to be consistent, or maybe just on the bottom. Let's write it on the bottom. All right, so so there exists a point C where G prime is 0. So G prime of C, there exists a C such that this is 0, which is f prime of C minus the stuff, which is f of b minus f of a divided by b minus a. And what does that mean? That means, if you look at this equation, that means f of c, there exists a point c in the interval between a and b where f prime of c equals to this stuff, f b minus f of a divided by b minus a. And that is exactly what we are trying to prove in the mean value theorem. Now, as you notice that this proof, I pulled this thing out of thin air. Where did you get this? Now, the way you get this actually is you beat around and look at, you're trying to use the Rolle's theorem. So you're trying to come up with some function such that it subtracts, becomes, the two ends are the same. Okay, and then its derivative has to come up with something like this. Well, actually, the derivative doesn't have to be anything. As long as you come up with a function where the ends are the same, and it's based on the function f, then the derivative will naturally you can use the Rolle's theorem and prove what's the quality of the derivative. And that is how this function is being worked out. Your book gives slightly different explanation of how to come up with this, but it doesn't matter how you come up with it. The point is, you obviously use what you're trying to prove in here, see? And then you beat around and try to get the two ends to be 0 by making arrangements and mess with it. But the point is, that is how the proof works, is we pull this thing out because it works, and yeah, it does. Now that's the end of the proof of the mean value theorem. Please put down the mean value theorem in your notes. Copy and paste it in your file so that because we will mention it later somewhat in our in the section, so that you don't have to flip back and forth all the time. Now the mean value theorem's application is very straightforward. So I will have you please look at example 4.15, where it says something about you need to find a function such that find some point such that the derivative equals to the slope. Well, what you do is you take the derivative and then make it equal to slope and solve for x, right? So, and that's very straightforward, and you don't, well, the mean value theorem tells you that such a point exists, but you can also figure out that the point exists by simply doing the calculations, right? So that's the problem itself is something that you can already do based on the knowledge you have so far. So please do that as your homework, example 4.15. And flipping over, and it's the same as 4.16. It's yeah, you don't really need the mean value theorem. You just need to take the derivative, set it to be the required value, and solve for x. And that's about it. The mean value theorem, however, guarantees that such a point exists. All right, so then that's that. Next, let's look at the corollaries of the mean value theorem. All right, let me clean off the board. Page 386, let's look at corollary 1. Please copy down all the corollaries in your note, copy and paste. And then that way, because we're not going to use the corollaries much in the rest of the section or the homework, but it will be mentioned in the next section. So it would be better if you don't have to flip around trying to figure out, oh wow, what is corollary 1 and what's corollary 2? Oh boy. So anyway, let's look at corollary 1. It's a cute little corollary with a cute little proof. It says, let f be differentiable over some interval if f prime of x equal to 0 for the entire interval. So the slope is 0, okay? All the way through. This thing, yeah, is anywhere you measure, the slope is 0. Then the f of x is a constant function. It equals to some number. It doesn't go anywhere. Now that might seem kind of obvious, right? And if you think about it, there's nowhere that it goes up and down, but we're going to prove it formally. So let's look at the proof. Now since f is differentiable, it is of course continuous. Now we're going to do a proof that's called proof by contradiction. That is, you assume that the statement is not true so that there's an exception, but the exception will lead to something absurd. And that's how we can prove that there is no exceptions. So let's say that there is an exception. F of x is not constant. So here are conditions. Okay, the condition is that f prime of x is equal to 0 for all x. The upside down means for all. Well, yeah. Anyway, so then let's say that at some point a of b, there are 2 points. We'll pick some point where if f of x is not constant, then we'll pick there are at least 2 points where f of a is not equal to f of b, right? Otherwise, it's constant if it's always equal. So there's at least 2 points that they're not equal. Now, given that these 2 points are not equal, then that means let's say a is less than b. Okay, somebody needs to be less than the other, so we'll just call a less than b in our example. Then f of b minus f of a divided by Not equal. I said not equal, right? So fb minus fa over b minus a, this is a value that isn't 0. For one thing, it's well defined because the denominator is not 0. A is not the same as b. But more importantly, being that these two values are not the same, this fraction is not 0. Now we're going to apply the mean value theorem. The mean value theorem says that if you have something like a function like this is differentiable and everything, then there exists some point C between A and B such that f prime of C is going to be equal to this thing right here. Okay, the mean value theorem states we'll find there exists a function, there exists a point C such the slope is the same as the slope of the rise over run of the whole thing. All right, now the problem, and this value is that f prime of C being equal to this is not 0. However, we already said f of x is 0 for all of x. So this contradicts our assumption that is always 0. Therefore, it is not possible that f of a is not equal to f of b for any ab in the interval. And that's how the corollary 1 is proven. So that, to repeat it, it means if you have a function where the derivative is 0 for all of x, then the function has to be a constant function. It's a constant function. The function is just f of x equal to some number. So next, let's look at corollary 2. Corollary 2 says if f and g are differentiable over some interval, and the derivative are the same, then they're only different by a constant. All right. So let's look at the second theorem, corollary 2. So corollary 2 involves two functions, f of x and then g of x, such that where the condition is that they have the same slope all the way through for the entire interval that we're interested in. Okay, and then so how would you prove that what are we trying to prove again? Then f of x is just g of x plus some constant. So to prove is f of x is simply g of x plus some number, constant number. Now how would you prove that? We will use the corollary we just used. We just proved corollary 1, and then we also set h of x a third function. We'll call it f of x minus g of x. So there's your third function, and what are we going to do about it? Now, being that f of x and g of x has the same derivative all the way through, then we can show that h prime of x is equal to 0. It equals to f prime of x minus g prime of x, which are the same. Therefore, h prime of x is 0. Now, if h prime of x is 0, then by the first corollary, what did I say? By the first corollary, by the first corollary, that means h prime of x is equal to some constant, okay, which is equal to f of x minus g of x. So f of x minus g of x equals to some constant, which is what we were trying to prove. F of x is equal to g of x plus some constant. And that's the proof of the second corollary. And then there's one more corollary we need to prove. Flip the page. Next, corollary 3. Let's see. Corollary 3 says that let f be continuous. This is on page 387. Next page. So let f be continuous over some closed interval ab and differentiable over the entire interval ab. So if f prime of x is bigger than 0 for the entire interval, then f is an increasing function. Similarly, if f prime of x is less than 0 for the entire interval of a from a to b, then f is a decreasing function. All right. Now that makes sense because f prime is the slope. If the function always have positive slope, it's always going up. So the function itself should be increasing. Imagine a hill where where you stand, the slope is upwards. Whereas if the slope is downwards all the time, then of course your mountain is your hill is decreasing as you walk. Now, so that seems pretty intuitively obvious, but we're going to prove it officially. And we will only prove the first one because for f of x bigger than 0, because the other one is identical. And we're going to prove, again, this time we're going to prove by contradiction. That is, we'll assume the opposite and then show that an absurd result will occur if if it's not increasing. All right, so let's look at that. So to summarize, what we're trying to prove is that if f prime is bigger than 0, that's what we're given. If f prime is bigger than 0 for all of the interval a, b, then f is increasing. That implies f increasing. Okay, I'll draw up arrow to mean that it's increasing. Now to prove that, suppose f is not increasing. Let's assume that suppose f not increasing. In that case, what does that mean? That would mean that at least there are some point in the interval okay. Well, your book used the interval and then used the 2 points that are the same. So the original a and b, we'll call it a1, b1. That's the endpoint. Okay, that's our entire interval. That is, the interval goes from a to b. Here's our interval. It goes from a1 to b1. Now if f is not increasing, then there will be something inside here, at least 2 points, such that f is decreasing. We don't know where the 2 points are, but so we will have fa and fb. Suppose f is not increasing, that means at least there is some kind of a and b such that f of a is bigger or equal to f of b. Now remember, this is bigger than 0 means the theorem says that function f is strictly increasing. So there is never even a time that they're the same. It's always gonna go up. So let's assume that is not true. Then that means there's a point where f of a is gonna be bigger than or equal to f of b. A and b are some points in here that satisfy this condition. All right. Okay, so now f is differentiable, so we're going to slap on the mean value theorem. What was the mean value theorem again? The mean value theorem says this. Okay, given all the conditions, things are differentiable, etc., there exists f prime of c, which equals to fb minus f of a over b minus a. That's the mean value theorem. Let me not start talking about the other one. The mean value, the MVT states this, okay, which is fine. And then what? So that means that now let's look at this thing. Now, being that fa is bigger than f of b, okay, this value bigger than or equal to, this is positive. This value is negative, right? Is negative or 0, being that f of a is bigger. So then this whole thing is going to be less than or equal to 0. But that contradicts this fact that we gave, because we already said that f prime of x is bigger than 0. It can for entire interval of a1, b1. So then, so this is a contradiction to, and therefore our proof is correct. The proof is done. Therefore, f must be the strictly increasing function through the entire interval that we considered. Then for the decreasing function, the proof is identical. Okay, you just flip the signs of the bigger than, it becomes smaller than, and then the whole thing works exactly the same way. All right, so that's the end of section 4.4. For homework, please do the examples I mentioned earlier, as well as page 388. I'm not going to go over the homework myself, because the homework don't directly apply the mean value theorem. It sort of applies in only telling you that you can find the answer, which you can find anyway. But it's still good to do some homework. So I have assigned some problems, which many of them are quite short. So homework on page 388, please do page number 159, 63, 65, 71, 73, 75, 77, 79, and 192.